All right, we are back. We're going to start talking and discussing free fall, which is pretty exciting stuff. Now we're going to be dropping objects. So here we go. A few rules in that about free fall and the acceleration of gravity. Anything that is free falling is basically any object that's falling just under the influence of gravity. So we are totally ignoring air resistance here. It's just assuming that the object is falling by itself due to gravity. All right, on Earth, we always assume then that the acceleration of gravity is negative 9.8 meters per second squared. Something you're going to have to get very used to, that number. All right, the only reason that massive objects will fall faster is because they'll have more air resistance present. But that is something that we will often neglect. So for these free fall questions, we're assuming there's no air resistance whatsoever. The object is just falling. So if you look at this diagram right here, you have an air-filled tube versus a vacuumed out tube. So totally no air whatsoever. When we drop a rock and a piece of paper at the same time in our regular environment, obviously the rock hits the ground first and the paper takes its sweet time to hit the ground due to air resistance. But if you take away air resistance, everything falls at the same acceleration. Therefore, the rock and the piece of paper fall completely at the same acceleration and hit the ground at the same time. We're so not used to thinking this way, though, because there is air. But for our calculations in class, we're all about the idea that there is no air resistance. In fact, you can prove it to yourself. If you take a textbook and put a light piece of paper above the textbook and drop the textbook, the paper and textbook will fall at the same exact acceleration. And the reason for that is because air resistance isn't affecting the small piece of paper because the textbook is blocking the air. Take a look at this. I know we said that the acceleration of gravity is about negative 9.8 meters per second squared. And the reason it's negative is because we like to say that the acceleration of gravity is always downwards towards the ground. But if you round that up to 10 here, you'll see that after 1 second, it's 10 meters per second. After 2 seconds, it becomes about 20 meters per second. And you see that the constant acceleration occurs, getting faster and faster and faster. And of course, that's in a no air resistance situation, because eventually you hit terminal velocity where you can't go any faster because the air is pushing up on you. But we'll get into that more as we go through it. If we want to calculate the distance an object falls, all right, and we start from a position of rest, meaning our initial velocity is 0 because we're holding it to start with, all right, the amount of distance that the object falls is actually very related to the time in seconds. So the formula, one of the Fab Fives that we'll use, is this bad boy right here. Because our initial velocity would be 0, this would cancel out, and literally you'd be just left with figuring out your displacement or distance that the object travels, and by knowing the time, we could solve for that. Why? Because we already know that the acceleration of gravity is going to be negative 9.8 meters per second squared. Take this picture again. After so many seconds, there is a consistent amount of meters that an object falls. And again, if you don't believe it, plug it in to that Fab 5 equation from the previous slide. And you could calculate for 1, 2, 3, 4, 5 seconds and see that no matter what the object is, if there's no air resistance, they all fall basically at the same acceleration. Now for free fall questions, we can use our Fab 5s once again. You've seen this slide before. Nothing new here. So as long as you look for your variables, what you have and what you're looking for, pick the best Fab 5 equation to make it work. There are some helpful hints when we're doing free fall. First of all, we always assume that gravity on Earth is negative 9.8 meters per second squared, the negative saying that we're going downwards. But don't forget that if an object is dropped from an elevated height, we can assume that the initial velocity of that object is 0 meters per second. And that's because you were holding it in your hand. It wasn't moving until you let it go. A couple hints that we can take from free fall problems is one of them, first of all, if you look up here, if an object is thrown straight up into the air and then lands back in the same spot, we can assume that the initial and final velocity will end up being equal in magnitude but opposite in direction. So if you look over here, if this girl throws up the ball initially at 2 meters per second, and we'll say that's positive 2 meters because it's going up, then if the ball comes right back down to her hands, right before it touches her hands, it would be at a negative 2 meters per second for final velocity. So same magnitude, as we said over here, equal in magnitude, just opposite in direction. So that is one of those hints / assumptions that we'll often need to make in order to help solve a problem. Also, another thing we have to consider is if you throw an object straight up into the air, so it goes up, 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 we know that as it's going up, it is slowing down. Why is it slowing down? Because gravity, or the acceleration of gravity, is acting on it, going in the opposite direction. So at the very height or peak of the throw, just before the ball stops and starts falling back down again, technically the velocity at the very top of the throw is 0 meters per second. So you can make that assumption as well quite often to help solve your problems. All right, if we have an example here of a falling stone. So the stone is at the top of the building, and after 3 seconds, it falls down to here. So we have a time of 3 seconds. We have, because the ball is dropped from the top, its initial velocity is going to be 0 meters per second. It is asking about the displacement, which we don't know. But is there any other information that we know about this problem that can help us solve? Well, we don't know the final velocity, but we can make an assumption about the acceleration since it's falling. We know that gravity's acceleration is always negative 9.8 meters per second squared. So now all of a sudden we have 3 variables that we know and 1/4 variable we're solving for. I don't know about you, but this to me looks like I might be using a Fab 5 problem. Let's go to the next part, the next slide, and see what we have for some work here. And here you have it, just what we did previously. We assumed the acceleration was negative 9.8, and we had an initial velocity of 0 because we dropped it, and the time was given to us. All of a sudden, we have those 4 variables we either have or looking for, and velocity final has nothing to do with the problem. So let's plug that into a Fab 5 problem. The equation I would use for the Fab 5 would be this one that doesn't involve velocity final at all. If I plug in my 0 initial velocity, that cancels that out, and I plug in my assumed acceleration and time, I end up solving for the problem algebraically and get a negative 44.1 for my displacement. What does a negative 44.1 really mean? It means that the displacement is negative or downwards because the object was falling, which totally makes sense, which is why for acceleration it was important to have that as a negative acceleration because it was downward. Gravity's acceleration is always negative 9.8. Even when the object's moving upwards, the acceleration of the gravity is just moving against it. How about this question where we have to toss a coin up in the air? We do know that it has an initial speed of 5 meters per second. We want to know how high it'll go, so we're looking for the displacement. We do know that when you toss a coin into the air, at the very height of the throw, its final velocity will be 0 because we know that assumption from one of our hints previously, I should say. And since acceleration of gravity is working against this object, acceleration is negative 9.8 meters per second squared. So you have 1, 2, 3 given variables, 1 that we assumed but still given, and 1 unknown that we're looking for. So now we don't have anything to do with time. So time is that thing that we will avoid in our Fab 5 equations. Let's look at the next slide to see how we plug that all in. And just like we said and did, we are looking for displacement. We have acceleration because we assumed it. We know the final velocity because we assumed it was 0 at the top of the flight. And we know the initial velocity is a positive 5. The only thing we don't have is time, so let's look at the Fab 5 we can use for that. The Fab 5 equation we're going to use is this one. And of course, we could move it around if you wanted to do and separate and isolate displacement by itself, and that's what I did here. So displacement's now by itself after some algebraic moves. I'm going to plug in my final velocity is 0 meters per second squared. My initial velocity is that positive 5. My acceleration of gravity that I assumed was negative 9.8. After I do all the algebra and take the time, you can pause this and try it out on your calculator, but you end up getting a positive 1.28, which makes sense that displacement is positive because the displacement was going up when you toss the coin in the air. Here's one last concept. If you have a pellet in part A and part B, which one would strike the ground maybe smaller, greater, or the same speed as part A? So we're comparing the two. If you throw this object up into the air at the top here, the pellet will be at 0 meters per second. So it'll start at 0, it'll come down to here, and it will be now at 30 meters per second, because we know that in a path, if you throw something up in the air, and it comes back down to the same, it ends up being the same magnitude velocity, just in the opposite direction. So if pellet B is thrown with a negative 30 meters per second velocity, and pellet A here is thrown up in the air and falls back down to this spot and starts at negative 30 meters per second, or downward 30, then they end up hitting the ground at the same exact speed. Because the only difference is, instead of just throwing it downwards at 30 meters per second like it is in part B here, this one went up, stopped, sped back up to 30 meters per second, and then went back down. So they end up being at the same speed at the bottom. So we talked about free fall problems today and the couple assumptions that you can make. Remember, acceleration of gravity is always negative because it's downward, negative 9.8 meters per second. So from there, as long as we take care of our vector quantities and we plug into our proper Fab 5 equations, we can have a really easy time solving these problems with very little data actually, because we can make quite a bit of assumption. Have a great one. Thanks for listening.